9.5 years and 3.26 billion miles. New Horizons is finally making its closest flyby of Pluto tomorrow.
NASA's New Horizons probe revealed something impossible about Pluto. This frozen world at the edge of our solar system defies every law of planetary physics we thought we understood. What they discovered challenges the fundamental rules of how small, distant objects should behave in space. When New Horizons transmitted its first close-up images in 2015, scientists stared at data that made no sense. Pluto wasn't the dead, frozen rock they expected. Instead, they found an active world with flowing glaciers, erupting volcanoes, and a molten core that shouldn't exist according to planetary physics. The impossible reality is that Pluto generates internal heat equivalent to objects 10 times its size. This violates the basic principle that smaller celestial bodies cool faster and stay cold longer. Yet Pluto burns hot beneath its surface, maintaining geological processes that should have died billions of years ago. To understand why this discovery breaks physics, we need to examine what makes Pluto so fundamentally wrong. Located 2.9 billion miles from the Sun, Pluto receives less than 1% of Earth's solar energy. At these distances, surface temperatures plunge to -229 degrees Celsius. Water ice becomes harder than granite. The only substances that remain flexible are exotic ices made from nitrogen, methane, and carbon monoxide. According to thermodynamic laws, an object Pluto's size should have lost its internal heat within 100 million years of formation. The dwarf planet is roughly 2/3 the diameter of our moon, with only 18% of Luna's mass. Every model of planetary cooling predicts Pluto should be geologically dead, but New Horizons data revealed the exact opposite. The probe's most shocking discovery was Sputnik Planitia, a heart-shaped region of smooth nitrogen ice spanning 600 miles across. This plain shows zero-impact craters, indicating the surface regenerates constantly through active geological processes. Spectroscopic analysis revealed convection cells beneath the ice, proving heat flows upward from Pluto's interior. The convection patterns form polygonal cells visible from space, each roughly 20 miles wide. These cells require sustained internal temperatures of at least -200 degrees Celsius to maintain the nitrogen ice's plasticity. For comparison, that's 100 degrees warmer than Pluto's surface temperature. NASA's thermal models calculate this heat flow requires an internal temperature approaching 1,000 degrees Celsius at Pluto's core. This is impossible for an object that should have frozen solid 4 billion years ago. The mystery deepens when examining Pluto's atmospheric dynamics. New Horizons detected active sublimation processes converting solid nitrogen directly into gas, creating a thin but measurable atmosphere extending 1,000 miles into space. This atmosphere varies dramatically as Pluto follows its elliptical 248-year orbit. During closest approach to the Sun, Pluto's atmospheric pressure increases by 300%. The dwarf planet essentially breathes, expanding and contracting its gaseous envelope in response to solar heating. But the energy required for this atmospheric cycling exceeds what Pluto should receive from solar radiation alone. Spectral analysis revealed atmospheric escape velocities that indicate internal pressure sources driving gas outward from the surface. This suggests underground reservoirs of pressurized volatiles requiring sustained heating mechanisms to maintain their liquid state. Perhaps the most physics-defying discovery was Right Mons, Pluto's massive cryovolcano. This ice volcano stands 3 miles tall and stretches 90 miles across its base. The summit shows clear evidence of recent eruptions, with fresh deposits of water ammonia slush covering older terrain. Right Mons represents an impossibility. Cryovolcanism requires subsurface oceans of liquid water mixed with antifreeze compounds like ammonia. Maintaining liquid reservoirs at Pluto's distance from the Sun demands continuous heat input equivalent to radioactive decay from elements like uranium or thorium. But Pluto's composition, determined through density measurements, contains insufficient radioactive materials to generate the required heat. The dwarf planet is roughly 70% rock and 30% ice, similar to Neptune's moon Triton. Yet Triton, which is larger than Pluto, shows no signs of internal heating or geological activity. The enigma multiplies when considering Pluto's relationship with its largest moon, Charon. These two objects orbit so closely that they're tidally locked, always showing the same faces to each other. Charon sits just 12,200 miles away, roughly 3% of the Earth-Moon distance. This proximity creates extreme gravitational stresses that should generate tidal heating through flexural deformation. However, calculations show tidal forces between Pluto and Charon are insufficient to maintain the observed geological activity. The energy budget doesn't balance. NASA scientists discovered that Pluto's heart-shaped feature, Tombaugh Regio, sits directly opposite Charon on the dwarf planet's surface. This positioning suggests a mass concentration that affects Pluto's rotational stability. Gravitational mapping reveals Sputnik Planitia contains a positive mass anomaly, indicating denser material beneath the nitrogen ice. The mass anomaly points toward the most radical explanation for Pluto's impossible behavior. Subsurface ocean models suggest Pluto harbors a liquid water ocean 100 miles deep, sandwiched between its rocky core and icy outer shell. This ocean would contain twice as much water as all of Earth's oceans combined. Maintaining liquid water at Pluto's temperature and pressure requires exotic chemistry. The ocean likely contains high concentrations of dissolved salts and organic compounds that act as antifreeze. Ammonia concentrations could reach 30%, lowering the freezing point to -100 degrees Celsius. But even antifreeze solutions require heat sources to remain liquid. The leading hypothesis involves serpentinization reactions in Pluto's rocky core, where water chemically reacts with iron-rich minerals to produce heat and hydrogen gas. However, these reactions typically occur in the presence of flowing water and specific mineral compositions found on larger worlds. New Horizons also revealed Pluto's surface composition defies chemical evolution models. The dwarf planet displays a complex mixture of nitrogen, methane, and carbon monoxide ices arranged in distinct geographical regions. Spectroscopic mapping shows these materials migrate across the surface following seasonal cycles tied to Pluto's orbital period. The most striking feature is the dark red coloration covering 30% of Pluto's surface. These regions, nicknamed Cthulhu Macula, contain complex organic molecules called tholins formed by radiation processing of methane and nitrogen. The tholin chemistry requires specific atmospheric conditions and continuous methane replenishment from internal sources. Methane has a limited atmospheric lifetime under solar radiation, breaking down into heavier hydrocarbons within 300,000 years. Pluto's persistent methane atmosphere indicates active outgassing from subsurface reservoirs, providing additional evidence for ongoing geological processes. The implications of an active Pluto extend far beyond planetary physics. If dwarf planets can maintain internal heat and subsurface oceans for billions of years, the number of potentially habitable environments in our solar system infinite solar system increases dramatically. Current surveys have identified over 2,000 objects in the Kuiper Belt, Pluto's home region beyond Neptune. If even a fraction of these worlds harbor subsurface oceans, they represent unexplored biospheres that could have evolved independently for 4 billion years. The discovery also challenges our understanding of planetary formation and evolution. Traditional models predict that objects Pluto's size should experience rapid cooling and geological death within 100 million years. Yet Pluto demonstrates that small worlds can remain active through mechanisms we don't fully understand. Perhaps most remarkably, Pluto's geological activity may be increasing rather than decreasing over time. Crater counting analysis suggests surface renewal rates have accelerated within the past 10 million years. This implies Pluto's internal heat engine is strengthening, not weakening, as the dwarf planet ages. The strengthening activity could result from gradual changes in Pluto's internal chemistry or orbital mechanics. As Pluto follows its elliptical path, gravitational interactions with Neptune and other Kuiper Belt objects could inject energy into the dwarf planet's interior through complex resonance effects. New Horizons continues its journey deeper into the Kuiper Belt, having already encountered the contact binary object Arrokoth in 2019. The probe's extended mission targets additional Kuiper Belt objects, searching for similar examples of impossible geological activity in the outer solar system. Each new discovery reinforces the lesson that Pluto taught us. The universe operates by rules more complex and surprising than our models predict. What we dismissed as a frozen dead world turned out to be one of the most geologically active places in the solar system. The physics-breaking reality of Pluto forces us to reconsider everything we thought we knew about planetary evolution. Small worlds can maintain internal heat through mechanisms that remain mysterious. Subsurface oceans can exist at distances where they should be impossible. Geological activity can persist for billions of years beyond what our models allow. NASA's New Horizons probe revealed that Pluto isn't just a dwarf planet relegated to the outer darkness of our solar system. It's a world that challenges the fundamental laws of planetary physics, harbors a subsurface ocean larger than Earth's, and demonstrates geological activity that shouldn't exist according to every model we've created. The impossible world at the edge of our solar system continues to rewrite the rules of planetary science, one physics-defying discovery at a time. What we found on Pluto breaks our understanding of how small, distant worlds should behave, revealing a universe far stranger and more active than we ever imagined possible.